Hello, today I will be walking through how to implement a queue with two stacks. So in this problem, you're given two stack data structures that you can use to create the functionality of a queue. So I will walk through two methods. I will start with one that has constant time pop operations and linear time push operations, and then one that has constant time push operations and actually amortized constant time pop operations. So I'll get started with the one with linear time push operations first. Okay, so the first method I have for implementing a queue with two stacks, I'm going to have the queue on the right side, and I'm going to just simulate what that queue's state should look like as we're adding items to these stacks. So I'll start out, and I'm going to add the value 3 to our queue, and we'll say that the bottom of this is the front of the queue, right? So I'll pop from the front, I'll push to the back, or I guess top in this case. And now the first thing we can do, we really only have one option. We can just push to one of our stacks. So I'm going to push to stack 1. And you can see in this state, if we pop, it's very easy to get the same value. There's no sort of complex algorithm required here, right? Because we just have one element. Things get a little trickier though as we start to add elements. So I'm going to add 3. I'll push it to the back of my queue. And here, how exactly should I go about pushing 8 into our simulated queue with these two stacks? Well, one thing we can do is we can use stack 2 as a buffer. So I'll pop from stack 1, push onto stack 2, and then push 8 onto stack 1, and then just reverse the process. So pop off of stack 2 and push onto stack 1. In this state, if I pop off of stack 1, I will get the value 3. And similarly, if I take the front of the queue, I will get the value 3, right? So it would be the exact same for those. 8 would move forward, and then the next value we'd pop off the stack would be 8, and the next value we'd get from the front of the queue would be 8. So we have the same state there. And you can see this continues. If I add the value 2 to the back of our queue, I can take these values, push them onto stack 2, push my value 2 onto stack 1, and just reverse putting those values back onto stack 1. So these are in reversed order. And so, as we take elements out of the queue and off of my stack, they should be the same. Now, the downside to this is every time you push an element on, right, it's going to be linear time to move elements from stack 1 onto stack 2, and then back from stack 2 to stack 1. So that is a downside, but pop operations are constant time, right? I can always pop off the top of stack 1, the same way I can just take from the front of the queue. All right, so we'll get started with method 2, which has constant time for push operations, but has an amortized constant time for pop operations, and I'll explain why, but it will be linear time for each individual pop operation that you'll see. Like the first pop operation, you'll see why it's linear time, but over time it amortizes to constant time, and I'll explain why in a bit. But we'll get started. So we're going to add our item 3 to our queue, the same way we did before. And all we're going to do is push that onto stack 1. Then we're going to place 8, our second value, onto our queue. And where we differ here from the last method is we're just going to push onto stack 1. We're going to continue pushing onto stack 1, so we aren't going to change over to stack 2 to keep the ordering. We're just going to push onto stack 1. And there will be some sort of housekeeping variables you'll need to implement behind the scenes. Like you'll need to keep track of, okay, what's the front of my queue? And the reason for that is, if I need to do a peak operation, I need to know that 3 is at the front. So how do we go about popping, right? This is where we have our linear time operation. When we need to pop, we actually are just going to move all elements from stack 1 onto stack 2. And we will return the top element of stack 2, in this case 3. So now let's say we need to push more elements onto our queue. We put 0 to the back of the queue, and we just push on to stack 1. How do we know here what the front of the queue is? Well, you just look at stack 2 and you see if it has any members on it, right? If it has members on it, those are the members that are going to get popped first. So in this case, 8 will get popped before 0. 8 should be what we return when we peak, and 8 should be what we return when we pop. So let's pop off the front of our queue. In this case, we'll take from stack 2. And let's say we need to pop again. We would do the same thing where we'd move everything onto stack 2, and we would pop this. So then, we'll continue this process, and I'll just really hammer it home with a few more examples, right? Adding 7, adding 8 back to our queue, adding the number 3. We're going to pop at this point. So we're going to pop 7. We'll push a few more numbers on. 9 goes there on the queue, and it goes to stack 1. 2 goes onto our queue, and 2 goes onto stack 1. If we need to pop here, we check stack 2 first to see if it has any elements, and we see it does, so we pop 8. This has constant time for pushing onto our stack, or our simulated queue rather, linear time for popping, but that gets morphed into amortized constant time, and I'll explain that shortly. All right, so I'm going to do my best to explain the amortized time complexity of the pop operation, right? The first time you do this pop, it's going to be linear time, but then for every subsequent pop, you are going to have constant time for all the elements that you already pushed onto stack 2. So I'll illustrate this. I'm going to push onto my queue and stack 1 simultaneously to show me setting up. And we'll do 5 items. So we'll do 0, 3, 9, 7, and 2. All right, so that was n operations, all constant time. Now let's say I want to pop, right? So I want to pop 0. I need to move all these over, which is 2n operations, because I need to both pop and push for each time, right? So 2n operations for the first pop, 2n plus 1, I suppose, and then for every subsequent pop, it's constant time, right? So let's say I'm popping all these, right? I pop these off, pop 9, pop 7, pop 2. So, with our first pop being 2n operations, but every subsequent pop being constant time, right? We can call that n operations for all the rest of them. We have 3n operations for all of our pops, right? Divided by n items that we're popping off. That divides to 3, which ends up being a constant time. So basically what that means is that on average, you're going to be spending a constant amount of time when you factor in that your first pop's going to be more expensive and all subsequent pops for all the elements you had on the queue are going to be constant time, right? O of 1. So that's kind of where it boils down. I know it's not as intuitive. It's a little bit harder to grok. So if you have any questions, don't hesitate to drop a comment, and I'll try my best to clarify as much as I can. Well, I hope you enjoyed this video, and have a great day. Thanks.